Hey y'all, in this video we're going to go over an example problem where a projectile is launched off from above the ground at an angle. So I consider this type 3 when I break this down into categories. So here we have a ball being launched at 20 meters per second at an angle of 25 degrees above the horizontal off a 15-meter high cliff. And this is going to be a series of 5 questions, and we're going to start with question 1 here of how much time does the ball travel for? So starting off, let's draw what's going on to get a good picture of it. So we have our cliff and we have a ball being launched up at an angle, and then it's going to, of course, fall down. This isn't a grade drawing, but you get the idea. All right, it's going to go up initially at 20 meters per second. That's what we got right here. And that angle above the horizontal, meaning this angle right here, is 25 degrees. Then we also have, so that takes care of this information, and we also have the height of the cliff. So here is going to be 25 meters. All right, so that gives us a nice idea of what's going on here. All right, let's go ahead and make a chart of the variables that we know to work with. So I'm going to make this in 2 columns, an X column and a Y column. Starting off with acceleration. For all the problems that we work out here, our acceleration in the horizontal is going to be 0. Meters per second squared, and then the vertical is negative 9.8. I'm leaving off units here just to save a little space on my screen. Then we know the for displacement is our next row. We don't know it for the X column, but we do know our vertical displacement is going to be a negative 25, and it's negative because this ball is going to be traveling down. So we're going to go ahead and put that negative in there to tell us that. Then for time, we don't know that for either column. And then for initial velocity, we can work those out. And then our last column, or last row, sorry, is going to be final velocity, and this is overlapping here. So before we get anything done, let's go ahead and find that VI, that initial velocity for both. And you're going to do that by using the 2 formulas we have, which is VIX equals VI cosine theta, and then the other one will be VIY equals VI sine theta. So what you're doing here is you're breaking down this initial 20 meters per second and breaking it down into how much is going up and how much is going over. This is vectors. So essentially you're saying here is VIX and then going up is VIY. So we've already done that this year. So going back to the formulas, you have VI is 20 meters per second times cosine of 25. And when you work that out in the calculator, you are going to get 18.1. And that is meters per second because it is velocity. So we can add that in here. And then for our VIY, it'd be 20 sine 25. And then when you do that, you're going to 8.45. And that is in meters per second as well. So now we have everything in our chart that we possibly could know at this point in time. So we can now move on to finding actually how much time we're going to work with. So let me pause and erase some stuff to make some room, and we'll keep going. All right, so now to find time, this is probably one of the trickiest things about these types of problems. So the formula we're going to use is going to be our distance formula, and we're going to use the vertical direction. So first I'm going to write our vertical formula, or sorry, our distance formula, and that's going to be our vertical distance equals our initial velocity in the vertical times the time plus 1/2 times our vertical acceleration times time squared. And the reason that I'm using the vertical information here is because we know this vertical distance or displacement. We don't know the horizontal displacement. So that's why we're choosing the vertical information. We know more in that table that I have now erased. We know 3 things versus the horizontal column. We only knew 2 things to work with. All right, so now we're going to fill in what we know. We know the vertical displacement that this ball falls from where it starts to where it hits the ground is negative 25 meters. That's going to equal our initial vertical velocity that we found earlier of 8.45 times the time that we don't know. We're going to solve for that. Plus 1/2 times negative 9.8 times time squared. So now my next step is going to be to just simplify this down and clean it up a little bit, which really just involves multiplying that 1/2 and that negative 9.8. So I'm going to bring everything else down. I'm actually going to remove this meters out of here just to make it a little cleaner looking for you. So 8.45 times time plus 1, or we're going to multiply 1/2 times negative 9.8 and get negative 4.9 times t squared. Now you notice that you have t in 2 places here, and that's a little tricky to solve for. What we're actually going to be doing is using the quadratic formula. Everybody learned it early in their math career, and now it's coming into play in physics. So we do need to rearrange this a little bit to make it easier to work with for the quadratic formula. If you're great at math and you can easily identify what number is A, B, and C for the quadratic formula, then feel free to not rearrange it. But I know for those of you that are not so great at math and may have difficulties, go ahead and rearrange this to set it up in the where A, B, and C are in the proper order. So I'm going to go ahead and do that for you, and I'm going to switch colors now. So first step is we're going to move this 25 over to the other side by adding it to the other side. So we're going to get 0 on this side equals 8.45t. All right, then we're going to have plus negative 4.9 t squared plus now 25. Then we're not quite in the proper order. For a quadratic formula, this t squared needs to be first. So we're just going to switch these 2 places. And since they're being added together, it's easy to switch them around. That's going to make our formula 0 equals negative 4.9 t squared plus 8.45 t plus 25. And now everything's in the proper order. And here we're going to have, this is going to be A, this will be B, and then 25 is C. So now it's easy to work with for the quadratic formula. All right, so now our quadratic formula is going to be our time is equal to negative B plus or minus square root b squared minus 4ac over 2a. And you're going to end up getting 2 answers from doing this. So I'm going to work out both. So what I'm going to do first is plug everything in, and you're going to get negative b, so negative 8.45 plus or minus the square root of 8.45 squared minus 4 times negative 4.9 times 25. And then that is going to be all divided by 2 times negative 4.9. All right, so now what I'm going to do is simplify this down to make it easier to work with. So I'm going to bring down this negative 8.45, and then I'm going to go ahead and I'm going to simplify everything that's inside here. And what that equals when you work this out in the calculator is 365.4. And then divide that, and I'm going to simplify the bottom here. 2 times negative 4.9 is negative 9.8. So all I've done now is simplify down, and I'm going to continue to simplify it down just one more time and get rid of the square root. And so when I do that, is going to be negative 8.45 plus or minus 19.11 over negative 9.8. All right. So now from here, you can easily solve both options, the plus option and the minus option that we have here. All right. Make sure at this point you do not divide this negative 8.9 by this negative 9.8. That is incorrect math. This top level of your problem is being added or subtracted, and that has to be done prior to dividing it by this negative 9.8. Don't make that math mistake. All right. All right. Sorry for that aside. Let's keep going. So the first time you work this out is going to be negative 8.45 plus 19.11 divided by negative 9.8. That is going to equal 10.66 on the top divided by negative 9.8, and that equals a negative 1.1. All right, for our second option, it's negative 8.45 minus 1911 divided by negative 9.8. That's going to equal negative 27.6 on the top divided by negative 9.8. and we're going to get an answer of 2.8. Now remember, this is equal to the time, so that's going to be in seconds for our answers. So like I said, you get 2 answers with this. Obviously, we've got 2 now. The one you're going to pick is going to be the positive one, because we're going forward in time, not backwards. So we do not care about the negative answer. So you work out 2, you pick the positive one. Every single time, pick the positive one. Okay, so this 2.8 seconds, going back up to our drawing, let's see if I can move this around properly. Just kidding. Sorry about that. If I can go back to my drawing, this 2.8 is from here and all the way to the ground. That is the 2.8 seconds that it went. All right, so that's it for question 1. Let's move on to question 2. All right, moving on to question 2. So now we are looking to find out how far the ball traveled horizontally. So what we're looking for in our diagram here is how far over this ball lands. All right, so this is a lot shorter than the first one. We're just looking for horizontal distance. So we're actually going to take the same formula we had before, our distance formula, but now we're going to use it in the horizontal direction. So it's going to be our horizontal distance equals our initial horizontal velocity times the total time plus 1/2 times our horizontal acceleration times time squared. So we're going to plug in what we know. We're going to solve for this horizontal displacement, so we're going to leave that alone. It's going to be equal to our initial horizontal velocity, which we found in the beginning of working all this out, and we found that that equals 18.1 meters per second. And then we're going to multiply that by the time, which we found in the first problem to be 2.8 seconds. And then the second half, our acceleration here is 0, so that cancels everything out that's being multiplied it, so we're only working here with 18.1 times 2.8. So we're going to multiply those 2 numbers, and we end up getting an answer of about 51 meters for our horizontal displacement. So that means this ball travels 51 meters horizontally as it from the edge of the cliff to where it hits the ground at. Easy enough? All right, let's move on to question 3. All right, so in question 3, we're looking for the final velocity that the ball's going as it hits the ground. Not once it's hit the ground and it stops. We want to know what the speed it's going to go right before it hits the ground. So I'm not going to redraw the whole diagram, just this end part of it hitting the ground. So the ball's fallen, it's coming down at an angle, here's the ground, and here's where it hits. We want to know this final velocity it is. We don't want to know just the vertical or the horizontal. We want to know the true final speed of the ball. So there's some of this velocity that is causing there's that horizontal velocity that we're working with that we're going to call that final velocity in the x direction. And there's the vertical component, and we're going to call that the final velocity in the vertical. And if we find those numbers, then we can ultimately find this number, or this velocity rather, by doing Pythagorean theorem. So let's figure out what VFX is and VFY is. So for VFX, that's an easy one. So you're going to use the formula 3 that's on your formula sheet, which is your final velocity, in this case in the x direction, equals your initial velocity in the x direction, plus your horizontal acceleration times time. Now, if you're thinking ahead, you're already one step ahead of me, you know that this is 0, so that cancels, meaning your final is your initial. So we initially had a velocity of 8.1 meters per second. I just put the decimal in the wrong spot. So that is also your final horizontal velocity. So I'm going to write that 18.1 up here. All right. Now for your vertical velocity, you're going to do the same formula, but now with the y direction. So VFY equals our initial velocity in the vertical direction plus our acceleration in the vertical times the total time that it's going. So we're finding this, so we're going to leave, just carry that down, equals our initial vertical, which was 8.5, minus 9.8, times our total time of 2.8. When we work that out, we get a final vertical velocity of negative 18.9 meters per second. Now we're going to write that down. So this negative tells us it's in the negative direction. This arrow is now telling us that. So this is just, we're going to carry over just 18.9 meters per second because this arrow is telling us the negative job, all right? So now we can ultimately find the VF by doing Pythagorean theorem. So we're going to have 18.1 squared plus 18.9 squared, and that will give us VF squared. So when you work all of this out, you're going to end up getting a final velocity of 26.3 meters per second. And that is what the ball will hit the ground at. All right, let's move on to question 4. So for question 4, we're looking for what the angle that the ball hits the ground at with respect to the horizontal. So what you're looking for is this angle right here. So what you're going to do is do a trig function. Inverse tan works great for this. So it's inverse tan, your opposite side, in which this case is 18.9, divided by your adjacent side is 18.1, and then solve that for the degrees, which is going to be 46.2 degrees. So just like we did the week we did vectors. All right. Let's move on to our last question. So for question 5, we are looking for max height. So let me redraw what we got going on here. So max height, we're looking for this height right here. We know this height was 15 of the cliff, but we want to know this height off the ground. So what we ultimately are going to do is use the distance formula with the vertical information. So it'd be our vertical displacement equals our initial vertical velocity times time plus 1/2 times our vertical acceleration times time squared. So that's going to, plugging in what we know, we're going to know our vertical initial velocity is 8.5 times time plus 1/2 times negative 9.8 times time squared, and that will give us our maximum height. So we don't know the time yet. We're going to solve for that. We don't want to use the 2.8 we've been working with, because that 2.8 is all the full time that the ball is traveling for. We want to know the time that it hits its maximum height at. So we want to know what it is here, not here. This is where the ball is at 2.8 seconds. We want to know here. So to do that, you're going to use the other formula that we use quite a lot, which is the final velocity is equal to the initial velocity plus acceleration times time. So at the top here, our final vertical velocity, if we set this as like the endpoint, will be 0 meters per second. So it'd be 0 equals our initial velocity of 8.5 plus negative 9.8 times time. We'll move the 8.5 over, equals negative 9.8 times time, and then divide. And then we get an answer of 0.87 seconds for our time to the top. So now we can come back up here and plug that in. So 8.5 times 0.87 plus 1/2 times negative 9.8 times 0.87 squared. So let me slide this over. And when we do that, we're going to get an answer of 3.7 meters. Now, before you think that's your final answer, look back at your drawing here. 3.7 meters is your answer that you got, but yet your ball's launched 15 meters off the cliff. That 3.7 isn't the maximum height. That's how high it's going from the cliff to the top. So this is 3.7 from here up to here. So the maximum height, though, is from the ground up. So we want this total height. So 3.7 plus 15 is what we want. So 3.7 plus 15 meters is going to be equal to 18.7 meters. And that's our maximum height. So just be careful on that. If you're solving it this way, that know that you're solving for the height that it goes above here, and that you need to add the height of the cliff. Okay? So that's it. I know this video was super long, and I know this stuff is confusing, so if you still need help, just reach out to me, and I'll be happy to help.